Hello to everyone. Welcome to the webinar. Thank you for joining us. We will start with a short welcome and introduction on behalf of EURCold, the European Working Group on Dams and Earthquakes, and the Young Professionals Forum. So we will just proceed with the first presentation. So this, we want to say, first of all, that this is the first webinar of a series that we intend to do in the future. It's based on the European working groups of the ICOLD European Club. We really appreciate the support of the ICOLD young professionals. This helps us to disseminate all the work that's being done in the ICOLD European Club internationally. In today's session, the European Working Group on Dams and Earthquakes has curated insightful presentations under the theme Advanced Seismic Analysis of Dams through 3D modeling. These presentations will be delivered by international distinguished experts. We would like to take the opportunity to make a very short introduction of what is the ICOLD European Club. The ICOLD European Club is one of the regional clubs of ICOLD. It consists of 27 European ICOLD member countries. It was established in 1995. Its main objectives are to encourage the formation of the European working groups, and also we conduct European symposia every 3 years to encourage cooperation and exchange of information between the European countries, to provide expert technical advice in relation to dam and reservoir safety, participate in public relation activities to explain the social, environmental and economic benefits of our dams, and of course to promote cooperation in professional training for young professionals. Now, to date, we have 12 working groups which have already completed their work. In this slide, you can see the active groups. We have 11 European working groups, task forces, and an ad hoc group at the moment. You can see their key focus areas on the slide. Their main objective is to interact and collaborate with ICOLD technical committees. At the same time, they organize meetings, workshops, seminars, symposiums, and now webinars. As mentioned before, every 3 years we conduct a European symposium. During this symposium, the European working groups have also the opportunity to conduct workshops. Now the European Working Group Chair Guillaume Veylon will make an introduction on the objectives of the group.
Thank you, Sera. So the European Working Group on Dams and Earthquake is 10 years old this year. And the aim is to promote, as Sera said, the exchanges between engineers and researchers working on the field of seismic analysis applied to dams. And to do that, we organize benchmarks, we try to share best practices, we provide some presentations, we work on reports, we organize symposiums on a selection of selected topics. The first symposium was held in Saint-Malo in 2016, and the most recent one took place in Athens in last September. It was a really nice two-day event with a lot of presentations, 34 at total, including 5 keynote lectures from international researchers and experts, and more than 70 active participants.
Okay, to stay updated with all the activities the ICOLD European Club conducts, we have a LinkedIn page. We also have an official website, and we issue an annual newsletter. The second issue is going to be distributed in a couple of weeks. We would also like to make a special mention, I would say, on the actions related to public awareness. In 2016, the ICOLD European Club issued the manifesto on dams and reservoirs. This document is currently being updated by the Italian Commission on Large Dams. It's going to be distributed in late May, along with the celebrations taking place for the Dams and Reservoirs Day, the 2025 edition. So in this final slide of this introduction, we would like to announce the Dams and Reservoirs Day, with the secondary title, Water and Energy Security for Europe. This initiative will be celebrated in late May, early June. Multiple events around Europe are going to take place. And we would like all of you to support us in this attempt to promote the benefits of dams. At this point, we would like to thank our speakers, all participants and organizers, and we think it's very important to mention that we need the support from the Young Professionals Forum, because it's giving us the opportunity to connect with young professionals worldwide, and this is an asset for us for ensuring a productive session and the sustainability of the profession. So at this point, I have the pleasure to give the floor to Mateja Klun, the YPF chair. Thank you.
Thank you. So good afternoon, good evening, good morning to everyone. Yes, we are very pleased to collaborate with European Club and looking forward also to the next webinars, not just this one today. I will just briefly say a few words about YPF. So we are established as a forum under ICOLD, and we are targeting young professionals in the early careers. And well, regarding the age, we are very specific. So we are targeting people who are below 40, who we believe are starting the career in the dam sector. But we are also very inclusive, inviting everybody to share expertise and always also looking for mentors, mentees, so on. Our general idea is to provide networking opportunities, to encourage and to mentor younger generations, and to find opportunities for us, for the young professionals, to gain knowledge, to gain expertise in a very interesting and very complex world of dams. We are also encouraging formations of the national networks, and until now 23 ICOLD countries have formed very active young professional networks within their countries, and we are supporting and hoping for this number to increase. There is more than 100 ICOLD countries, so this is also our target that we want to achieve. We try to distribute information about our activities, so we use the online resources. We have our own webpage, we have a YouTube channel where, for example, all of the recordings of the webinars are available, and we also have a LinkedIn group which has over 1,000 members, and we try to keep all of these platforms alive and active. Next slide, please. Our board, the ICOLD YPF board, consists of 7 members, 1 chair and 6 regular members. The term of office is 3 years, and I would just like to use this opportunity today to announce that soon we'll be opening a call. 2 positions will open for the next 3-year term, and we are seeking good candidates. So you have to be supported by your national committee, and the term is for 3 years, and you basically need to be motivated, need to be prepared to work with us, and you have to be under 40 years for the duration of the term. So if you are interested, you can contact us already online using email, but as I said, we will publish the call and you'll see the official information on how to get to be nominated to be part of the ballot in the call. And for the last slide, I just added some photos of our activities, and I will just say thank you. And I see a lot of people attending this webinar, which is very pleasing, and I hope you enjoy the technical content of this webinar. Thank you.
Okay. Thank you for the introduction, Sera, Mateja, Guillaume. And now let's move to the first presentation. So we proceed with this second presentation titled Understanding the Seismic Behavior of an RCC Gravity Dam Design in a 1G SEE Construction Area by Frederic Andrian and Maxime Vonie from the Artelia Group. Frederic Andrian from Artelia holds an MH in civil engineering by the University Joseph Fourier of Grenoble. At Artelia, he is technical director and project director for the Dams, Hydropower and Infrastructures business unit. And Maxime Vonie holds an MH in civil engineering from INSA, National Institute of Applied Sciences of Lyon. And at Artelia, he is civil engineer for the Dams, Hydropower and Infrastructure business unit. So please, Frederic, Maxime, the floors and the screen is yours.
Well, thank you very much. So we're going to try to share the screen. It's not this one. Yeah. Which one? C'est ça? Peut-être. This one. Tu vois, c'est l'inverse. F. Is it working? Yeah, it's working. Can we start?
Yes.
Yes, for sure.
Okay, so good morning, everyone. Thank you for attending this webinar. It's a real pleasure for Maxime and I to present to you the understanding of the seismic behavior of an RCC gravity dam designed in a 1G SEE construction area. So all the co-authors of the related paper are on the screen as well. It was already presented in Athens a few months ago, and the current version is a slightly extended version of that presentation. Right. So let's start with the general context of the project. So the project is located in the Philippines, in the Rizal province. It is called the Upper Wawa Dam, which is now completed, almost completed. It is located about 10 to 20 kilometers eastern of Manila, the capital. The primary function of the dam is the water supply. We are talking of about 700 million liters per day. The secondary function of the dam is the protection against flood, and it has already worked quite well because in last July, the dam was impounded in less than 3 days, if I remember, because there was a typhoon occurring at the area. So Artelia was acting as the subcontractor for the EPC contractor of the project for the static and the dynamic calculations of the dam. So about the main features of the dams, we are talking of a 85-meter high RCC gravity dam with a slightly curved layout. The crest length is about 400 meters. We have a quite thick profile of the dam with an upstream face slope of 0.6 h to 1v and the downstream face slope of 0.8 h to 1v. The curvature radius is quite high, about 500 meters. So on the left side, you have the plain view of the dam, whereas on the right side, you have a typical cross-section of the dam, highlighting the quite thick profile. Next slide, please. So geological context, we are in the context of sedimentary to metamorphic formations made of, let's say the substratum is made of interbedded sandstone and mudstone. Here on the pictures, you can see the thickness of the weathered layer, which was removed during the excavation works. a picture of some samples of core boxes. The interbedded mudstone and sandstone is rather massive, but with strength. We are talking of geological strength index of 65 and uniaxial compression strength of 35 MPa in average. As we are talking of the Philippines, the dam is constructed in a very high and severe seismic area in the connection between many tectonic plates. We are talking of a PGA of 1G for the seismic, the safety evaluation of quake. On the right side, you have the unified hazard spectrum, if I remember, along with the accelerograms, which were used in the calculations later. So the calculation have used what we call a state-of-the-art gradual approach. First of all, we have used a finite element model for the response spectrum analysis in order to assess the main eigenmodes of the dam in a linear elastic model with ANSYS. And then nonlinear time history analysis was carried out with FLAG3D in order to capture more realistic seismic behavior, including the dam contraction joints, the dam foundation interface, and all the dynamic interface interactions, including the foundation and the reservoirs, which will be detailed afterwards by Maxime. About the mechanical assumptions, so as for Artelia, we are talking of input data. We have not participated in defining nor in the determination of the parameters. So in the numerical analysis, the dam roller compacted concrete and the foundation bedrock are modeled with linear elastic constitutive law. The contraction joints and the dam foundation interface follow a column friction constitutive law with tension cutoff. In the tables, you have the main parameters. I will not go through in details. About the hydromechanical assumptions, the dam water interaction for the dynamic calculations were considered by means of compressible elements for the reservoir. Then the uplift were addressed as additional forces applied at the dam foundation interface according to US Army Corps of Engineer approach. Then the silt pressure is also applied as additional forces to the upstream face. And the sediments liquefactions were considered as well in the calculation. So let's start about, I think, one specifics of the carried out calculation. As everyone may know, concrete always endure shrinkage during and after hydration. And usually this shrinkage is not considered for the seismic analysis of concrete dams. So here we have decided, as we are in a quite severe seismic area, we have decided to consider this shrinkage in the calculation in order to assess the effect of this shrinkage in the seismic behavior of the dam. So the dam use a fly ash rich high workability RCC as per the definition of ICOLD Bulletin 177. So we have assumed a 70 microstrained stress relaxation creep in the calculation. In addition to that, we have considered as well 30 microstrain of shrinkage due to the, let's say, the seasonal temperature effect. So the total shrinkage considered in the calculation under static load case is about 100 microstrain. The average contraction joint spacing of the dam is about 18 meters, which leads to a theoretical 1.8 millimeter joint opening at the end of every shrinkage which occurs in the concrete. As you can see on the picture, you have the distribution of the contraction joint openings at the end of the construction of the dam. As you can see, we have an average value which is close to the theoretical value, but we have some peak values where we have, let's say, steep abutments of the concrete and where have wider spacing of the joints. So, as we have a loss of contact between the dam blocks under static load case, although it is actually quite low opening, this means that displacement is required to trigger the arch effect owing to the slightly curved layout of the dam under earthquake load case.
Okay, now regarding the dynamic assumptions, the model that we used to perform the time history analysis involves a compressible reservoir, which is directly connected to the dam and to the foundation. It also involves a mass foundation with a boundary condition representing the semi-infinite nature of the medium. And the earthquake loads are applied as equivalent stress wave directly at the base of the model for the time history analysis. Regarding the dynamic damping, a damping ratio value of 5% is considered for all the calculations. For the response spectrum analysis, the damping is directly included in the size spectrum input. And for the time history analysis, the damping is only considered within the concrete and not within the foundation. Okay, let's talk about the dynamic behavior of the dam, beginning with the response spectrum analysis. And we will begin to speak about the modal analysis. If you take a look at the first picture on the left side, you can see the model shape of the first eigenmode, which mobilizes 83% of the modal mass for a frequency of 3 Hz. And this model shape highlights the base rocking. And usually the critical eigenmode regarding tensile stress for gravity dam is the upper crest rocking. If you take a look at the right side of the first picture, you can see the model shape of this critical eigenmode for a random gravity dam, given as an example. But in the case of Wawa, the important thickness of the profile leaves no room to generate this critical mode. If you look at the second picture, you can see the vertical tensile stress distribution for the highest dam block. And you can see that the maximum stress is obtained at the dam hill and is about 2 MPa. And elsewhere, it does not exceed 1.5 MPa, which is lower than the concrete dynamic strength. Consequently, cracking is expected to be negligible when considering the potential opening of the dam hill, which is not possible here because the model is linear and the opening between the dam and the foundation is not allowed. But in case of opening, it will generate a redistribution of stresses. Now, regarding time history analysis results, we will begin to speak about compressive stress. On the figure, you can see the contour of the envelope of vertical maximum compressive stress computed during the earthquake for the upstream phase. And as expected for a gravity dam, maximum values are calculated at the dam hill and the dam toe. Here is a value of 4.8 MPa. And this is a direct consequence of the base rocking. But what you can also see highlighted in red in the figure is the presence of arching concentrated near the crest of the central blocks. And this is due to the slightly curved layout of the dam, which is activated only during the earthquake. What you can also see is that the value of 3 MPa is quite low, and this is due to the initial opening of the contraction joints due to shrinkage. Still for the time history analysis, but now about tensile stress. Given the important thickness of the profile of the dam, tensile stress are expected to be low, if not negligible. But as you can see on the picture, giving the contour of the envelope of vertical maximum tensile stress computed during the earthquake for the upstream phase, the dam body is subjected to unusual tension concentrating along the contraction joints. And we were quite surprised to see that. And to explain this behavior, we will show you a short video. Can you just tell me if you can see the video?
Yes.
Okay. On the video, you can see that tension is only visible during very short periods. And the explanation that we found is the absence of permanent contact between blocks during the earthquake, allowing them to move independently depending on the seismic loads. And this allows adjacent blocks to acquire different velocities during the earthquake when the contact is lost. And once the contact is recovered, it generates dynamic friction, explaining the presence of this tension along the joints. And once the velocities of the blocks, of 2 adjacent blocks are the same again, the stresses disappear and there is no more dynamic friction. Still for the time history analysis, regarding the dam foundation interface behavior, you can see that the minimum sliding safety factor that we computed is a value of 1.2. Consequently, sliding is not expected. However, as you can see on the picture, irreversible shear displacements affect for some blocks the wall contact area. As you can see here on the highlighted in red for one block of the contact, for one part of the contact. And this is not consistent with the safety factors value that were obtained by the calculations. And to understand this behavior, we made an analysis of the dynamic behavior, and it shows that sliding is not instantaneous, but gradually spreads from upstream and downstream. As you can see on the second picture, for giving the temporal evolution of the shear displacements for the block highlighted in red in the first figure. And consequently, safety factors can stay higher than 1 during the earthquake, even if the final behavior shows overall sliding. And to finish, the presence of sliding may induce irreversible opening due to dilatancy, and this may increase the permeability of the bedrock. And to take this into account, we did a post-earthquake situation with the following assumptions. The full uplifts are applied to the sheared area in contact with the reservoir, which is plotted here in red in the figure. And residual strength parameters are applied to the contact. And with these assumptions, a few blocks do not mathematically fulfill the stability criterions. As you can see on the picture, some sliding safety factor values are lower than 1. But a closer look shows that all the concerned blocks are side blocks and that the direction of the shear resultant is directed towards the center of the valley and not toward downstream. And consequently, sliding is not supposed to generate any uncontrolled release of the reservoir.
Okay, so a few words of conclusions. If I can recall the criteria according to ICOLD's recommendation, I believe we are talking about ICOLD 13148. The behavior of the dam is acceptable for SEE load case, even if there is any damage, as long as there is not any uncontrolled release of the reservoir. So when talking about this criteria, the Upper Wawa Dam, as designed, complies with the state-of-the-art criteria regarding earthquake load case. However, and the dam does not exhibit the usual upper crest rocking model shape, owing to very thick profile of the dam, which means that, let's say, the usual high tensile stress is encountered at the crest of the dam is not present here in the calculation. The arch layout of the dam also allows some key-in, which prevent from an overall displacement of the dam toward downstream and over sliding. Still, we have highlighted some, let's say, limitations in the behavior of the dam. One may think that the thick profile of the dam may be counterproductive regarding sliding because actually the mass of the dam is accelerated during the earthquake. So the higher the mass, the higher the seismic load. Then there is the question of the RCC shrinkage, which when combined with a with a high curvature radius is not compatible with the thick profile to trigger enough arching. And then there is a third concern, but which is not critical. It is the risk of water stop joint tearing during the earthquake event. As you can see on the bottom figure, you have the envelope of maximum opening during the earthquake, which may increase up to 1 centimeter. We believe 1 centimeter starts to be quite high for usual water stop joints of contraction joints. Next. So if we can suggest a few improvements in the dam design for future dam design under similar conditions, we believe it would be better to use shear keys in contraction joints to avoid the offset blocks during the earthquake, and then avoid dynamic friction between adjacent blocks. Then another improvement may be also to add a seismic belt at the crest of the dam in order also to prevent from any offset between the blocks. And maybe a solution, but which needs to be the purpose of detailed design, of course, would be to reduce further the curvature radius of the dam and reduce a little bit the thickness of the dam profile in order to adopt a more usual profile. And now we are going to show a video of the dam, which shows the behavior of the dam if the dam is equipped with shear keys. The top video and the bottom video as a comparison, the one without the shear keys. As you can see, there is not any red spots anymore on the upper video as a consequence of the added shear keys. Okay, so I think that was the end of our presentation. So thank you for your attention. And I don't know, Mateja, if it is now time for questions and discussions.
We'll have the questions and discussions at the end, but there will be time.
Okay. Okay.
So we proceed on seismic response evaluation of a CFRD, considering its precise 3D geometry and the surrounding valley by Emilios Comodromos and Panos Dakoulas. Emilios Comodromos is professor of civil engineering at the University of Thessaly in the domain of geotechnical engineering, structural engineering, and soil structure interaction. And Panos Dakoulas is emeritus professor of civil engineering at the University of Thessaly, and he's specialized in soil dynamics with focus on dams and port facilities. The presentation today is going to be given by Professor Comodromos. So, Emilios, the floor and the screen is yours.
Please, Mr. Comodromos, the floor is yours.
Yes. Okay, so I apologize for this inconvenience and this is trouble. It's probably due to the Teams, to the version of the Teams I have, but we found the solution. So now I presume that you can hear and see my presentation. And at first, I would like to congratulate the presidents of the organizing committee, Mrs. Sera, Lazaridou, Dr. Guillaume, Veylon, and Mateja, Klun, for this interesting event, and at the same time express my gratitude for the invitation to give this lecture. It is mainly based on the research that we carried out at the University of Thessaly, together with the Plug Power Corporation, with the aim to investigate the risk of concrete phase rock dams and the seismic action.
Excuse me, can I just, can I ask you if you can turn off the camera? I think it's a connection problem and it's also disturbing your sound. Maybe I think we will hear you better if you turn off the camera. Thank you.
Yes. Okay. Is that better now?
Yes, that's better.
Okay. So the focus is mainly on the response and the integrity of the concrete panel, because as we know, this is the most important issue for the safety of the dam. So we are carrying a comparative study for the behavior of the concrete phase rock dam. Next slide, please. So the analysis corresponds to the Mesochora Dam, which is a concrete phase rock dam. And as we know, the last decade we can see many 3D analyses, but in most cases we have in the analysis only the dam or a simplified V-shape for the apartments. Here we are focused on the comparative analysis, where we take into account the dam and the valley, or the dam only. In that last case, we consider that the behavior corresponds to the perfectly reached valley. Before going to the dynamic analysis, we have to establish the initial stress condition, and to do that, we carried out the multi-stage construction stages, then the creep, and after that, the effect of embowelment. Then we have the seismic analysis, and to do that, we used an hysteretic model. And for the hydrodynamic pressure, we applied two approaches. The one is the simplified Zankar method, and the other is the use of water elements. Further to the analysis that were presented in Athens last September, we carried also some additional analysis considering the high hysteretic model together with the more Coulomb failure envelope for the rockfill material. Can we go to the next, please? Next slide. So before presenting the results of the dynamic analysis, let me share with you the results we got from a comparative study of a 2D approach and a 3D approach. This concerns the NUM dam already presented by Andrian Dahl in 2019. And here we started with 3D analysis in which we have seen a very good agreement in settlements between the results of the analysis and the observed results. But on the contrary, when carried out the 2D analysis, we found considerably higher settlements. To investigate this topic, we plotted the distribution of vertical stresses of the 2D analysis. You can see that at the left, and the 3D analysis, you can see that at the right. So at the top of the dam, we can see that more or less we have the same rate of stress development. But when we move to the base of the dam, it is quite clear that the rate of the stresses developing the 3D analysis are lower than the 2D. We can see that also in the figure in the center, where we have the development of stresses with depth. It is quite clear that we need to move to deeper to achieve the same level of stresses. So to further investigate this effect, we plotted the evolution, the stress development across the crest of the dam. We can see that in the next slide, please. Here it is evident that there is some kind of hanging of the dam to the abutment, to the canyon, and we can see that with it is quite clear where we can see an increase of the stresses on the abutment and a decrease of stresses in the dam. And this is more important when we are moving to the base. At the right, we can see clearly that at the same level, we have considerably lower stresses in the dam. And of course, we can realize that further to the difference in settlements, we have difference in the stress developed in the dam. So we all of us know that the state of stress is also affecting the behavior in seismic action. Can we move to the next, please? Now, moving to our case at the Mesokora Dam, just we can see the cross-section at the mid-crest. The height of the dam is 150 meters, and it consists of a zone 3C at the downstream part. Moving to the upstream, we have the 3B zone, which is of better quality of the 3C, and just below the slab, the concrete panel, we have the 2B, which is very good quality of rockfill. Can we move to the next, please? Here we have the values using for the parameters for the plastic hardening model, which has been used for the construction, for the simulation of the construction of the dam. The concrete panels were simulated using the Liefenberg's constitutive law. Of course, we have used the characteristic value for for the resistance in compression and tension of the material. And when we moved to the dynamic analysis, we applied the hysteretic model. The initial shear modulus has been defined based on the in situ test, and has been found to vary with the mean stress. And so we propose two different equations to give the initial values to the material for the rockfill and the bedrock are given at the by the equation 1 and 2. You can see them at the right. And in addition to that, we finally applied the combination of the hysteretic model with surface failure for the rockfill material. The next slide, please. Here we have the fine difference grid we have used for the surrounding valley, the dam, and the panels. To the next, please. And here we can see, we can realize that the apartments were not planar. So we can imagine that we have an important interaction effect at this area. So it is something that we strain and focus to find out what the effect could be. To the next, please. Now, considering the concrete panels, we have 23 concrete panels, and the initial joint between them was 1 centimeter. After the construction of the panel, an enlargement at the side of the central panel has been made, and this is mainly done to avoid excessive compression stressor which takes place during the embowelment. I have to mention here that the thickness of 1 centimeter was involved with too many difficulties for the simulation. The first, it was a very refined mesh in this area, but we quickly overpassed that. We solved this problem with some algorithms we carried out and incorporating the process of the fine grid generation. The main problem was that the too many, excuse me, the too small size of the elements was the reason of a very low time step for the dynamic analysis. Initially, we calculate that using Rayleigh damping, we needed almost 10 days per second of input motion. So we have used many approaches to solve this problem. First of all, we tried to enlarge a little bit the size of the elements to 5 and from 5 to 10 centimeters, and obviously we solved the problem, but the interaction between the slabs was not accurate. So we left this option. I mean, we decided to use the 1 centimeter because the very important thing was the behavior of the concrete panels. The next slide, please. Here we have the presentation of how we took into account the hydrodynamic effect of the water in the dam. So the simple approach was to consider the hydrostatic pressure, and that forces using the simplified Zankar method. And the other option was to consider water elements. Within the process, we took into account both hydrostatic and hydrodynamic effect implicitly. The next slide, please. Now, because we are focused on the behavior and the response of the concrete panels, we set a 0 point, the time started, I mean, when we constructed the panels, and we consider that they are strengthened enough to take loads. So we can see at the figure on the left, the settlement due to the embankment and the remaining creep. I mean, the creep is depending on time. So you can imagine that during the construction, each layer has a remaining creep to keep based on the time and that was constructed. So we included that the analysis, and we accurately take into account the remaining creep together with the embankment. The settlement anticipated in the maximum settlement of the dam was approximately 42 centimeters, and the horizontal displacement, that means across the stream, was of the level of 35 centimeters. We can see it at the graph at the right side on the top. At the two graphs below, we can see the displacement and the settlement at the concrete panels. On the left, we can see the settlement obviously are the same as the dam, but a very interesting figure is the right one, showing the movement of the slabs from the side to the center because of the embankment. I don't know if you can see the numbers. The displacement is approximately, the maximum displacement is approximately 8 centimeters from the side to the center of the dam. Obviously, there's no move at all for the central panel. Very interesting is the form shape shown at the right part of the slide. And with the magenta line, we can see the deform shape just below the concrete panels. And it is quite evident that there is a strong interaction between the abutments, I mean the site of the canyon, and the dam. To the next slide, please. So now, here we have the dynamic analysis. This is the input motion. We carried out several input motion. Here we are going to show the results from the Lixouri, a town at the Cephalonian island. And we have to say that we try to use the smallest possible time for the analysis. So we found the range in which we have the 95% of the intensity of each input motion. For instance, here is between the second and the 8th seconds, and we run the analysis just for the 6 seconds because usually in a very powerful computer, it requested approximately 5 hours per second. And this was made possible using the Maxwell damping, which is 20 to 35, 30 times faster than the Rayleigh damping. The next slide, please. And here we have the first results. Here we are comparing the simplified Zanger method for the hydrodynamic effect and the results for considering water elements. Obviously, this corresponds to the case where we take into account the dam and the valley. We can see the response on the base of the dam with the red line. We can realize that it's more or less similar. There's no difference between them. On the contrary, we can realize that we have some differences for the crest, and the approach of Zanger seems to be more corresponding to a more stiff material, and this can be understood because the movement of the liquid is giving a more smooth pressure on the concrete panels than the Zanger method, in which we consider the concentrated masses on nodes. The next slide, please. And here we have the comparison between the two methods for the minimum principal and the maximum principal stress. We can realize that the case with water elements provide us slightly more compression stresses. At the same time, we can see that at the bottom right figure, and when we're comparing the minimum principal stresses, you can realize that the case where the Zanger method was applied is giving some kind, very small, but some kind of tensile stresses at the side of the dam, and we have not the same case where we consider the water elements. This is the top right figure. The next slide, please. Here we have the comparison of the results of the response acceleration when we consider the dam and the valley and only the dam. Once again, we can realize that the behavior at the base of the dam is more or less the same. On the contrary, at the crest we have some differences and some peak value in the case of the dam only. Obviously, in the case where the dam was considered, we considered fixities at the base of the dam, and this is rendering, I would say, the behavior more stiff. The next slide, please. And here we can see the displacement. With the A, where I mentioned the case including the valley, and with B, the case corresponding to the dam only. At the top left, we can see the relative displacement. That means the difference of displacement between the crest and the base. And we can see that the case including valley provide slightly higher displacement. And this is the same for the stresses. We can see at the top of the right, the dotted line corresponding to the case, including the valley, that we have slightly higher stresses. When examining the slab behavior, we can see that in the case of the valley and the dam, we have higher displacement difference, I would say, between the base of the slab and the higher point. That means the relative difference between is higher. That, and this is corresponding to the angle that we have as some kind of turning of the concrete panel. Obviously, is 2 times higher than the case where we consider the dam only. The next slide, please. And here we have the stresses developed in the concrete panels in the case of the valley and the dam only. We can realize that in the case we consider only the dam, we have larger compression zone. This is shown at the top right figure. And we can realize that at the bottom left, we can see the stresses corresponding to the valley and the dam, and at the bottom right, we can see those corresponding to the dam only. We can see clearly that when we consider the dam only, the stresses are higher, and this should be attributed to the fact that we consider fixities at the base of the dam, so the dam is more rigid, that in the case more stiff than in the case we consider the interaction between the valley and the dam. The next slide, please. And here we have the last analysis. This was not included in the presentation in Athens last September. So for the rockfill, we consider, together with the hysteretic model, we consider a failure envelope for the material. So at the right figure, we can see the response at the base of the dam, and we can see that it is more or less the same. At the left side, we can see, which corresponds to the crest behavior, we can see that the acceleration corresponding to the hysteretic model is higher than the case in which we also take into account the Moore-Coulomb envelope. That means we gave the possibility to the material to plastify it. And as we know, the plastification provides the ability for higher absorption of energy. That means to realize less acceleration mode, but at the same time, we have an effect on the displacement. We can see in the next slide, please, that the displacement we have in the case of Moore-Coulomb are higher, mainly the remaining displacement. We can see on the graph at the left that the range of displacement in the x direction, that means across the stream, is more or less the same between the two approaches, the hysteretic model only and the hysteretic in conjunction with the Moore-Coulomb failure envelope. But however, the remaining is almost double in the case of the Moore-Coulomb option. That means where, in the case, we are giving the possibility to the material to be plastified and absorb more energy. I have to remind here that the positive effect is that we have less acceleration. On the right side, we can see more or less the same thing at the base of the dam, and the difference between the base and the crest is given at the right bottom graph, where we can see that the case of combination of high static model and the Coulomb provides us also 2 times the value corresponding to high static model. I should emphasize that this behavior, this difference, is more important in the case of a crest, because at the crest, the materials have the possibility, I mean, the stress applied at this level in conjunction with the resistance of the material give the possibility of higher plastification than in cases where we have higher mean stresses. That means the surface of failure is larger and can give higher resistance to the material. And this brings me to the end of my presentation. I apologize for this trouble to not provide the presentation from my computer, and with the trouble of not having at the same time the images and the explanation. Thanks for the attention.
Thank you, Professor Comodromos, and sorry for the connection problems. And now we move to the Q&A season that is going to be facilitated by Mateja, Klun, and Guillaume Veylon. So if you have any question, please write it in the chat.
So we already have quite a few questions in the chat. I can start by reading the first one. Yeah.
Thank you. Thank you all. Thank you a lot. I think it's time to end the seminar. And I thank you once again, every attendee for their participation, and the speakers for sharing their work. And thank you all, and have a nice day.
Just a short announcement before we close. There is an upcoming event taking place in the capital of Bulgaria, Sofia, between the 9th and the 12th of April. This is a workshop of this is the 17th ICOLD International Benchmark Workshop on Numerical Analysis of Dams. The general organizer, it's Technical Committee A of ICOLD, Computational Aspects of Analysis and Design of Dams, chaired by Antonella Frigerio from the Italian committee. The local organizer is the Bulgarian committee. You can see this is the flyer. These are screenshots from the flyer. There is an optional tour on the last day. And of course, you can find a lot of information at the Bulgarian committee's website. So from our side also, thank you everyone. Thanks to the presenters, to this. Thank you for participating and for your contributions in this event. Also, I would like to thank the co-organizers as well. And we would be very happy, please follow us so that, and we will be very happy to see you in our next webinars. Bye everyone.
Thank you to everyone. Bye-bye.
Thank you. Thank you.
Bye-bye, everyone.
Thank you, everyone.
Thank you.